Hey everyone, so this is going to be our first sort of lesson here. Basically what we're going to do right now is we're just going to do a repeat from Friday, from those of you who are absent, or if you just kind of don't remember what we did, we're going to run through that. So to do this, we're just going to run through the notes. If you took notes on Friday, then all this kind of filled in, so you can kind of just follow along if you'd like, or if it made a lot of sense to you at the time, you can kind of skip through this lesson. We're just going to go through series circuits, like the rules for those, and then how to set up and do a VIRP short problem for the series circuits. Alright, so we've got all of our equations now, and at this point we need to put it all together and use it to analyze some type of circuit. So this is sort of the most basic circuit we can have. We've got one of our circuit diagrams like we talked about. Here's a battery. This is the symbol for battery on your reference tables. Here's a resistor. Just something that's going to slow down that electrical current and provide some resistance so it doesn't get too large. So for this problem, a 9-volt battery is connected to a basic circuit with a 100 ohm resistor as shown in the diagram. Okay, first off, you got to be able to draw those ammeters and voltmeters the correct way. So draw an ammeter that would measure the current through the resistor. Remember, those ammeters go next to the device. So if we're drawing in an ammeter, we're just going to throw that right on the diagram, directly next to it, right in the line of the circuit. You could do it before or after the device. Either one is fine. On the diagram, draw a voltmeter that would measure the potential difference across the battery. So those voltmeters, if this helps you remember it, VIP, voltmeters go in parallel, which is kind of like the physics term for going around the device. So it gets connected on one side of the battery. That V in a circle is our symbol for a voltmeter, and then gets connected to the other side of the battery. And then to do some calculations here, to calculate the current moving through the circuit. Alright, let's think about what we know here. We've got 9 volts. That sounds like a voltage, or a potential difference is 9 volts. We have 100 ohms of resistance. That sounds like R, going to be 100 ohms. And we're solving for current, which remember is I in these equations, measured in amps. Alright, take a look at your reference tables. See if you can find an equation with all these things in it. The one I'm looking at is R equals V over I. Okay, R is 100 ohms. I'm not going to show all my units. I'm having a little trouble writing on my screen right now. Equals 9 volts over I. Solve for I, and I got a current of 0.09 amps. That's what that says, 0.09 amps. Cool. How much power is used by the resistor for part D? Okay, well, now we're going to look at our power equations for circuits. Yeah, we can use any version where we know all of the things. If you take a look at those equations, I'm looking at VI, just the first one right there. Again, I'm not going to substitute with units because I'm having trouble writing, but I got 9 volts times a current of, I think we just found that over here, 0.09 amps. Alright, 9 times 0.09 is, I think, 0.81, and the unit for power is watts. And so what we've got here, when we have one of these circuits, is just a bunch of electrons that gain energy and lose energy. And so these electrons, they gain their energy from the battery, they gain their voltage from the battery. So they gain 9 volts, they travel around the circuit, and they lose 9 volts of energy. Then the electrons are tired, so what are you going to do? If you're out of energy, you go back to the battery. And then you gain 9 volts, and then you lose 9 volts. And then you gain 9 volts, and then you lose 9 volts. These electrons are sort of just traveling the circle of gaining energy, losing energy, and then gaining it, and then losing it, and then gaining 9 volts, and then losing it. So that's what happens when you have one of these circuits actually connected. This is this process of gaining the voltage and then losing that voltage. This was a simple circuit, only had one device and a single battery, but now we got to look at having multiple devices. So what would happen if you had multiple resistors? We'll take a look. Okay, so for this class, we're going to look at 2 types of circuits. We've got series circuits and parallel circuits. You need to know the difference between them, like be able to identify one versus the other when you look at it, and you need to be able to sort of use that information to solve the problem the right way. So we'll start with series for this one. Objects in series follow each other along a single path. So, when you think of a series, like a series of books or a series of movies, it's like one after the other after the other. And that's exactly what you would have. You start at one place, these electrons. You travel, and you have to go through one resistor, and then the next resistor, and then the next resistor. It's along and this is the important characteristic here, a single path. So imagine you were one of these electrons traveling along. Would you have a choice as to which ones you wanted to go through? In other words, as you travel along our wire, you have to go through resistor A, and then you have to go through resistor B, and then you have to go through resistor C. At no point there did you have an option. At no point did you get to pick which resistor you wanted to go through. That's what makes this a series circuit. A parallel circuit is any sort of circuit that has multiple paths. So if you were an electron and you walk in the start, and these would be all wires connecting 3 different devices. They could be light bulbs, it could be resistors, it could be anything. And you have a choice here if you're going from start to finish. You can go through resistor A, you can go through resistor B, or you can go through resistor C. The fact that you had multiple paths, sort of an option as to which way you wanted to go, did you want to take path A or B or C, is what makes it a parallel circuit. With that in mind, pause the video, give number 34 a shot, see if you can figure out which of these circuits are series and which of them are parallel. Hopefully you paused it and gave it a shot there. So, let's go one at a time. For this one, you start the battery. The battery gives you all of your energy, gives you all of your voltage. So if you're an electron, you're all excited you got 12 volts of potential difference, 12 volts of energy. And we're going to pick which way we go. Do you want to go through the 6 or the 3? And it doesn't really matter because the fact that you had that choice, that you can go through the 3 or you can go through the 6, that's what makes it a parallel circuit. Again, if you're an electron, see, once you reach this point right here, you can go this way or that way. That's what makes this parallel. Alright, here in the middle, I'm going to start, I'm an electron, I'm traveling, alright, I'm going to go through this resistor, I'm going to go through that resistor, and then I'm going to go to the battery. Looks like that was all a single path. There were no sort of options there, no choices. And so this would be a series circuit. Last step, alright, I'm an electron, I go through the first one, I go through the second one. Oh man, it looked like that was all one path. So it's another series circuit. Alright, in a series circuit we have multiple devices and they add up to some sort of total resistance. So in series, having resistors follow in a row, it's like extending the length of a single resistor. It's like making a long, thin road even longer. It will increase the resistance. Because imagine this, you're an electron, and now all of these ohms of resistance, they tire you out. They are resisting you. So as you go through the first one, alright, that's 2 ohms of resistance. Oh man, you gotta go through another 2 ohms, and then another 2 ohms. That's a lot of resistance you had to go through. If we had to take the total of all of that, well, 2 and then 2 and then another 2 gives you a total of 6 ohms of resistance, right? Because 2 and 2 and 2 makes 6. We have a word for that total resistance. It's called the equivalent resistance. It's called that because 2 and 2 and 2 is equivalent to 6. So you can almost sort of effectively replace all of these individual 2 ohm resistors with a single 6 ohm resistor. That equivalent resistance, if you don't like that term, you kind of just think of it as the total resistance, right? The total of 2 and 2 and 2 is 6. So let's take this and we'll see if we can sort of fit it into a single circuit. So 2 resistors connected to a 9-volt battery, the way they're shown. Find the equivalent resistance. Okay, so for each of these parts, I don't know, see if you can give it a shot before I kind of go over them. So for part A, find the equivalent resistance of the circuit. We got a 1.5 ohm resistor and a 3 ohm resistor. And if you had to find the equivalent resistance, or remember, it's just another way of saying the total resistance, I would say it has a value of, alright, well, 1.5 plus, 1.5, there we go, plus 3 gives you a total, or an equivalent of, I'm going with 4.5 ohms. There we go. So again, the idea is that just 1.5 is equivalent to 3. I'm sorry, 1.5 and 3 is the equivalent to 4.5. Alright, for the current. Remember that's I in these equations. That's what we're looking for. We know a voltage here. So and we've got a couple of resistances. The equation I'm kind of looking at is Ohm's law. R equals V over I. Let's plug in what we can here. So we know that V is 9 volts. We're solving for I. And here's kind of a trick. We've got a lot of different resistances now. We've got this 1.5. We've got the 3. And we've got this 4.5 that we just solved for. Which of them would we use? I'm going to use the 4.5. And the reason I'm doing that is this 9 volts is the total voltage. And we always need to be consistent in physics. If we're using the total voltage, then we should use the total resistance, just to be consistent. And when you do that, you get, cross-multiply carefully, I got 2 amps here. And it's important that you use the correct resistance, or you'll get sort of the incorrect current there. Alright, is it possible for more charge to flow through the 1.5 resistor than the 3 ohm resistor? The answer to this one is going to be no. Can't be done. Here's why. Think of this think of this wire. It's like a one-lane road, right? If you're traveling down the road and you're like a car in the back, you're going this way. You're at the 1.5 ohm resistor. And let's say there's a car in front of you on the road. Maybe it's like around the turn a little bit. And that car is also traveling the same path. On a one-lane road, could the car in the back go faster than the car in the front? No, because you can't get around them. They're in front of you. They're blocking your path. And that's kind of what happens in a series circuit. All the electrons have to travel at the same rate. Now remember, the word we have for that is current, the rate at which this charge flows. So the current is the same through all of these devices. And that'll become important in a couple of minutes. If we want the potential difference in this 1.5 ohm resistor, alright, we're going to use Ohm's law. I gave you the equation there. So let's plug it. R equals V over I. R is going to be 1.5. That's a 1.5. Equals, we're solving for V, and that current is going to be, I think, 2 amps. Because again, we just said the current's the same everywhere. I'm going to throw in the 2 amps here. Multiply carefully here, and you get V is equal to, I got 3 volts for part D. I'm going to do that same math over again for part E to find the potential difference in the 3 ohm resistor. And again, I told you we're going to use Ohm's law for this. R is the 3 ohms, V equals, V is what we're solving for, and again the current is the same everywhere, so I'm going to plug in actually just that same current, and you get a voltage of, I got 6 volts. Alright, and here's why we did this, or here's what's interesting here, is if we take the voltage through the first device and the second device, let's think about the total voltage that was used. In other words, one of these resistors uses up some voltage, 3 volts. The other uses up more voltage, 6 volts. 3 and 6, what's the entire voltage there? 9 volts. And the reason that's important or interesting is, remember, what was the voltage of the battery? 9 volts. And so each of these devices uses up some of the voltage. And together they use all of it. Okay. So what we just did there is we used a couple of our circuit rules, even though we didn't really go over it. Meaning all of these different sort of symbols and variables have a relationship with one another. And here we're just going to sort of clarify them all, so that if that previous part didn't make a whole lot of sense, that's okay, because here's going to be our rules here. Now you have to be familiar with these, but you do not need to remember them because they're all in the reference tables. Alright, let's start with current. So all of these different devices can have a different current. What I mean by that is this 1.5 ohm resistor has some current moving through it. The 3 ohm resistor has some current moving through it. The battery has some current moving through it. How are they all related? Well, we tried to make a big deal out of that before. The current through all of these devices is the same. So in a series circuit, the current is the same in all devices. Meaning the current through the battery is the same as the first one, is the same as the second resistor. Now, your reference tables do have this written out, but they have it written out mathematically. And the way that they chose to write it is like this. I equals I1 equals I2 equals I3. And you can have sort of any number of devices here, so they just give like a dot dot dot, meaning, oh god, that's a lot of dots. I mean, this could just kind of go on forever. As many devices as you have, they all have the same amount of current moving through them. Alright, resistance in series. What I mean by this is, just before we used the two individual resistances to find the total resistance. We did that up here. We said that we've got a 1.5 ohm resistor and a 3 ohm resistor, and we used it to find the total resistance. Oops, let's put that in brackets. So, as a mathematical rule, we'll say that the resistances add up to the total. And again, the term we have for that is the equivalent resistance. It's just kind of the physics term that we use for the total resistance. The reference tables has this written out for you. It's written in this form. Req, meaning the equivalent resistance, is equal to R1 plus R2 plus R3. And again, you can kind of do this for as many resistors as there are. And the voltages. We kind of tried to, we looked at this rule just before. We've got one device uses up 3 volts, the other uses up 6 volts, for a total of 9 volts. So if we had to state this in a mathematical rule, I would say that the voltages add up to the total. And for our purposes here, when I say total, I really want you to think of the battery, because the battery supplies all of the voltage to the circuit. So, in your reference tables, this is written in the form V equals V1 plus V2 plus V3, and again, this could kind of go on for as many devices as there are. In your reference table, again, they're all right here. If you go to your electricity page, here's all the equations that we've done so far, and then we've got our series circuit rules, which we just covered. For current, again, it's the same in every device. The total current through the circuit is equal to the first current, is equal to the second one, is equal to the third one, and so on. The total voltage is equal to the first voltage, added to the second one, added to the third, and so on. So the voltages all add up to the total, and the resistances all add up to the total. Just make sure if it's a series circuit, you're looking at these rules right here, and not the parallel rules, which we'll talk about in another lesson. So let's finally put this all together into like a problem, like something I would ask you to be able to do. 36. Draw a circuit with a 3 ohm resistor in series with a 6 ohm resistor. The circuit is connected to an 18 volt battery. Alright, so let's just draw it first. Oops, and then we're going to calculate the current through the 6 ohm resistor. So when I draw this, I'm going to draw, actually let's change my color a little bit. Let's go pink. Oh right, so we've got our battery, which is our 18 volt battery here. And we are connecting it to a 3 ohm resistor in series with a 6 ohm. So what I would look for is in a series circuit, you have 2 resistors connected to a battery, and it's all in a single path, meaning that if I trace it with my finger, which I'll do right now, if I follow along, I should never have the opportunity to turn along a different path. So this one looks good. Yours might look a little different. Again, as long as it's all connected and in a single path, then you did it right, and you're good. Now, here's kind of the problem when we talk about circuit analysis. We've got a bunch of different pieces of information here. We've got this 3 ohm resistor, a 6 ohm resistor, and an 18 volt battery. Now, each of those has, or could have, a different resistance, a different current, a different voltage, or use up a different amount of power. So, if you're keeping track, that's 4 things. That's V, that's the voltage, the current, the resistance, and the power for 3 different devices. That's 12 different things I could ask you for. So it helps to have a way to sort of stay organized through all of this. And what I'm going to suggest that you do is set up a VIRP chart. You guys will like this. So I could ask you for, again, the voltage, the current, the resistance, or the power for any of these devices. VIRP. Now I could ask you the voltage, the current, the resistance, or the power through the first resistor. We'll just call it R1, just to give it a name. I could ask you any of those pieces of information through the second resistor, or I could ask you for the total amount used by the circuit. And again, when I say total, I really want you thinking battery here. Okay, so I'm just going to fill out a chart like this, just to keep us all organized. And I'm going to fill in kind of just whatever I can for now. So, let's go. Alright, I mentioned something about 3 ohms. Well, ohms sounds like a resistance, so I'm just going to call it the resistance of the first one, meaning the resistance of R1. I mentioned 6 ohms. Let's throw that in here, because it's the other resistor. Has a resistance of 6 ohms. 18 volts. Alright, well, that 18 volts sounds like a voltage or a potential difference. So I'm looking at this column, and again, when I use the battery, I want you to think of the total used by the circuit. So I'm going to throw that in down here. Let's figure out what we're solving for. I want the current, which is I, through the 6 ohm resistor. So the 6 ohm resistor, I want I through the 6 ohm resistor. I want to find this box right here. I may not be able to find it right away, but again, that's what I'm asking for. That's what we got to find. So let's start with how this chart works. For this chart, you can move up and down these columns using our circuit rules. And when I say circuit rules, I mean these guys in the reference table. In other words, the total resistance is all of the other ones added up. The current's the same everywhere. The voltages add up to the total. So we'll use that to fill out columns. To fill out rows, meaning like, horizontally, we'll use Ohm's law, R equals V over I. We're going to use Ohm's law a lot for this unit. It's kind of just using the same equation over and over and over again. But we have to stay in our same row when we do Ohm's law. In other words, if I'm interested in R2, I can only use values in this row for R2. So I can use the 6 ohms for R2. That works great. But I cannot use that 18 volts. The reason I can't do that is it's the total voltage for the circuit. Not all 18 volts were used up by the 6 ohm resistor. It would be wrong to say that. So we're going to have to just kind of think our way around this. And the way you would do that is just look for something you can solve, like anything. Even if you don't know why or how it's going to be helpful, just like find a thing that you can fill out. If you know most of a row or column, you can fill out the rest of it. So I'm looking at, see this 3 ohms and the 6 ohms. I think we can use that to find the total resistance. 3 and 6 is a resistance total of 9 ohms. Okay, that's something, right? It's good to, know more than we did. But again, I don't think that's going to help us find this current right here. So we gotta, let's find something else we can solve for. I'm hoping you're looking at this box right here, the total current. Because I know I crossed out the 18 before, but I don't know how to erase that. So in this row, I think we know V and we know R, and we can solve for this current right here. I'm going to do Ohm's law. I'm just going to use the one that I wrote out right here. The resistance is 9 ohms, and again, I really want to point out here, see how I'm staying in this row right here. 9 ohms resistance, the voltage is 18, equals, again, 18 volts works, and we're solving for I, and when you do that, I think you get a current of 2 amps. So I'm just going to fill that in here, right? Again, it's not the box I was looking for, but it's something. And then for this next one, just as you do more of these, you get a little more used to it. it seems like we don't have a lot to go with here. But this current is a really useful thing to know in a series circuit. The reason for that is, jumping back to the reference table, the current is the exact same in every device. So I can just fill in all these currents. 2 amps, 2 amps, and at that point I'm done, right? Because weren't we just looking for this box right here? Since they all have the same current, again, we're good. 2 amps, that's it. Cool. So for all of these problems, anything with multiple resistors, any of these circuits, I want you to make this VIRP chart. If you get really used to this, and you find you don't need it to get the question right, then alright, then I guess you can move away from it. But particularly since we're doing this online thing, and I'm not there to help you guys, just try making this chart. As soon as you see it's like a multiple device circuit, because I think it'll help you. I think it'll help you organize everything. So what I'd like you to do is try question 37. Pause the video, give it a shot, and then I'll go over it in a couple minutes. So take this chance, pause the video, but I'll go over it right now. Alright, hopefully you've given it a shot, but right now I'll go through it. So we're going to, it says to draw the circuit. If I ask you to draw the circuit, then let's draw it. Draw a circuit with 10 ohm resistor connected in series with an unknown with a resistor of an unknown value and a 24 volt power source. Alright, I'm going to start with the power source because I normally like doing that. We are in series, so we're looking for a single path. So anything with a single path and 2 resistors in it. So I'm just going to, draw them on the same part of the wire. Oh god, that turned out atrocious. Come on. There we go. This is pretty terrible. But it'll work. Okay, I was just going to sort of write in all of the values that I know. In other words, we know that one of these is a 10 ohm resistor. You don't have to write the values next to the thing, but I find it helps keep me organized. We've got a 24 volt power source, so this it provides 24 volts of potential difference. It says that this resistor has an unknown value, so I'm just going to write an R equals question mark, just to as a note to myself that I don't know it. That's a question mark. Okay, the current through the circuit is 1.5 amps. So we've got a current moving through it of, again, current is I, 1.5 amps. It says through the circuit, so that sounds like that's probably the total current. And we want the resistance of the unknown resistor. Okay, if you looked at this and you got stuck and you didn't do a VIRP chart, then I'm mad at you online. I'm virtually mad at you. We're going to do the VIRP chart, and we're going to have our different devices. R1, R2, the total. And then I'm just going to kind of fill in my grid lines. So again, you should be doing this if you're staring at the problem with a blank sheet of paper. Make the VIRP chart. And then just kind of fill in what you can. Again, we know that one of these is 10 ohms, so I'm just going to fill that in here. 10 ohms. We know that the power source was 24 volts. And again, that power source or the battery we're going to use as this total row. Oops, I'm sorry, it was 24. There we go, 24 volts. I said the current through the circuit is 1.5 amps. Again, to me that sounds like that's the total current through the circuit. So let's give this a 1.5 amps. Alright, we want the resistance. The unknown resistor. So it always helps to really clearly identify what we're solving for. I think we want the resistance of that other resistor. So we want R for that one. So this is what we're looking for right here. And again, this is kind of like what's something that you can solve for, even if you don't know how it's going to be helpful. There is more than one way to solve this. But something that I want to sort of pop out at you is this current is a really helpful thing to know in a series circuit because, again, it's the same. It's the same everywhere. Looking right here, all the currents have the same value. So I'm going to fill in 1.5s here. I don't know how that's going to be helpful, but maybe it will. We'll see. All right, what's another thing that you can solve for, even if you don't know how it's going to be helpful? Well, see how I know V in this row, and I know I in that row? That means we can find R for that row. Again, I don't know how it's going to help, but let's just kind of fill it in. We know that R is equal to V over I. If you want full credit on the regions, assuming we have regions, then make sure you show all the work of the equation. V is 24 volts, I is 1.5 amps, and again, I'm just getting that right from this row right here. When you solve through, I got 16 ohms. Okay, well, I was going to fill that in here. Okay. And again, now we're just going to look for anything that we can solve for. And I'm kind of specifically looking at it. So you see how one of them was 10 and the total is 16? Well, 10 plus blank makes 16. 10 plus 6 makes 16, right? Because 10 and 6 makes 16. And that's it. That's our answer. So, I don't know, let's circle it in... let's go yellow. There we go. Alright, last step for this one. I'd like you to give question 38 a shot. Again, draw the circuit, make the VIRP chart, and then give it an honest effort. Pause the video, give it your best effort, and then if you get stuck, then hit play, and I'll sort of guide you through it. Alright, question 38. Draw a circuit with 3 resistors. Okay, it's a little different, but we're going to sort of apply the same strategy that we had before. We've got 3 10 ohm resistors connected in series with a 36 volt battery. We're going to calculate the total power consumed by the circuit. So, alright, I told you to draw it, so let's draw it out. We've got a battery, we've got 1, 2, 3, oh god, 3 resistors. Connected to a 36 volt battery. So again, it sounds like all 3 of them are 10 ohms. So I'm just gonna 10 ohms, 10 ohms. Again, you don't have to write this next to it, but I recommend it. It just helps you organize yourself. Whoop, 36 volt battery, and this should sort of become second nature to you as soon as you see one of these circuit analysis problems. We're gonna make a VIRP chart, but this one has not 1, not 2, but oh god. But 3 resistors and then the total. So it's just 1 extra row. It makes it look like more work, but it's not actually going to be that much worse. Okay, so now I'm going to fill in what I know and identify what I'm looking for. So what do I know? I know 3 10 ohm resistors. Okay, so let's go a different color. I like this pink color. So let's go with 10 ohms. 3 10 ohm resistors. So they all have a value of 10 ohms. And the 36 volt battery, again, that battery is the total voltage. Cool. And I want the total power consumed by the circuit, the rate at which it uses up energy. Well, that's P. That's this power. So I ask for power pretty rarely. It's definitely going to be the least common thing that I ask for. It'll show up every once in a while. Alright, let's find it again. We can't solve for this directly, right? Because we're solving for P. P equals question mark, but we don't know. Again, we have to stay in this row. We just don't know a lot in that row. So let's find like something, anything that we can find. I'm hoping that 10 and 10 and 10. This kind of pops out at you that the total of those is 30. 30 ohms, our total resistance. Okay, that says 30 ohms. Now, for that power, okay, well we know V, we know R, and we're solving for P. Well, as long as you know any 2 things here, you can always fill out that last one. What I mean by that is we have those power equations in the reference tables. It's this whole mess, right? P equals VI equals I squared R equals V squared over R. Now, I'm just going to walk through these. Do we know V and I? I don't think so. We know V, but we don't know I, so that's no good. I squared R, well, kind of the same problem. We don't know I, so I'm not going to use that one. V squared over R. Do we know V and R? Okay, I think that's the case, right? We know V, we know R, we're solving for P. So that's what I'm going to use. P equals V squared over R. 36 volts squared over 30 ohms. Okay, 36 squared over 30 is... I don't know. I don't have a calculator. 36 times. I got 43.2. Whoop. And the unit for power is watts. 43.2 watts. I apologize, this is kind of a mess, but that's it. That's what we're looking for, right? So again, a lot of blank space in our chart, and that's okay, because again, we're only looking to get this guy right here. And that's our VIRP chart for series circuits. The next lesson we'll do kind of the same thing. We're going to take this whole VIRP chart and apply it to parallel circuits, which again, the chart will work, it's the same strategies, but a slightly different set of rules, which you could probably tell by looking here. So that'll be the topic of our next video.